Operating a furnace is a big job. Good furnace operation pays off in cost savings and safety. One way that furnace operators minimize costs and maximize safety is by following proper startup and shutdown procedures. In general, startup preparations for a furnace are tasks done before the burners are lit. One thing you'll need to do is check the status of the furnace with your supervisor. If the furnace has been shut down for maintenance, you'll have to verify that the work's been done and that the furnace can be prepared for startup. You should also make sure that all the tag-outs have been lifted and that the equipment is in its normal pre-start condition. A furnace and the area around it should be kept clean to minimize safety hazards. If there are any tools left around, or rags or other flammable materials, they should be stored or disposed of properly. Before you start up a furnace, it's a good idea to inspect inside it. For instance, examine the tubes and the refractory. Check the tubes for bulges and signs of cracks or holes. If a flammable process fluid leaks out of a cracked or ruptured tube, it could ignite and create a dangerous operating condition. The tubes should rest on their supports and not hang freely or sag. The tube supports should be in good condition. If they're loose or broken, they won't hold the tubes properly. Also, inspect the refractory. Look for cracked or loose bricks and mortar. Any of these problems can affect the insulating properties of the refractory and reduce the efficiency of the furnace. It's also a good idea to check for loose debris in the furnace and remove any you find. If you notice any damage, report it. The damage may have to be repaired before the furnace is started. During the startup preparations, all access openings should be closed up tight. These include all the peepholes, doors that provide access for tube headers, and any other places that could allow air leakage into the furnace during operation. If you spot a potential air leak, report it. When a furnace is operating, air should enter only through the burner air registers. If the registers don't open and close like they should, it will be difficult to regulate airflow, so it's important to check them for proper operation. Another thing you should take a look at is the stack damper. Make sure it's not stuck or broken. You'll need the stack damper working properly to control airflow through the furnace. Often, the air registers and the stack damper are left wide open during the pre-start to prepare for purging. A pre-start procedure we'll cover in a minute. In addition to the air supply system, the fuel supply system should also be checked, and the valves should be lined up prior to startup. In general, lining up valves means verifying that they're in the proper positions. There's often a line-up checklist that indicates how each valve in the system should be set. While you're lining up the valves, look for leaks and signs of valve or piping damage. Detecting and repairing problems at this point can help prevent equipment damage and injury. The valve lineup often calls for the isolation or block valves and the pilot valves for the individual burners to be closed. There may also be blinds in the fuel and process fluid lines. Blinds are basically discs that are inserted into the lines to prevent fluid from flowing to certain areas of a process system. Blinding the fuel lines prevents fuel from inadvertently reaching the furnace before the burners are lit. But if there are blinds, at some point they'll need to be removed so you can get fuel to the furnace when you need it. With gas-fired furnaces, there are often knockout drums that have to be drained of moisture that may be in the fuel gas. Moisture in the fuel can cause combustion problems in the furnace. Also, a lot of water in the fuel can put out the fire at the burner. So it's important for the fuel gas to be free of moisture before it's ignited. There may be more than one knockout drum to check. At this facility, there's a knockout drum that serves the entire facility, and there are knockout drums for individual furnaces. For oil-fired furnaces, you'll need to check the oil system components to make sure they're working properly. For example, look at the pump that moves the oil through the system, and the oil heater, which warms the oil to make it easier to atomize. Any obvious indications of damage or defects should be reported. Also, check the oil strainer that removes impurities from the fuel oil. The strainer may have to be cleaned, or the strainer baskets may have to be replaced. For many furnaces, the last thing done before lighting the burners is purging. Purging the furnace removes any combustibles or unburned fuel. Unburned fuel can explode when the burners are ignited. Because of this, purging is one of the most important steps in getting a furnace ready for startup, and it has to be done thoroughly. Furnaces are typically purged with either steam or air. This furnace is purged with steam. The steam is injected into the furnace and it carries any flammable vapors out through the stack. This system has permanent steam lines that are open to start steam flow to the furnace. You should purge as long as your operating instructions require. It may be necessary to purge until you see steam coming from the stack, or even longer. In many cases, furnace startup actually begins with establishing the flow of process fluid or charge. This step should normally be done before the burners are lit. Otherwise, the empty tubes that carry the process fluid could become overheated by the burner flames. Control valves regulate the charge flow in a furnace, and establishing the charge flow involves properly lining up the valves in the process fluid system. In multi-pass furnaces, there's often a separate valve arrangement for each pass, so you'll need to check the valve positions in each pass. For this furnace, a pump is started to get the process liquid circulating. With the pump running, the control valves for the process fluid are set as needed. The flow is verified by checking the appropriate instrumentation. If the process fluid is a gas instead of a liquid, you may need to start a compressor rather than a pump to establish flow. A furnace may seem most dangerous when it's operating and flames are burning inside. In fact, many of the furnace explosions that have occurred happened during startup when the burners were being lit. So it's critical to follow procedures carefully when you're firing up a furnace. The first main step in lighting the burners is to light the pilots. To be safe, the operator checks that all the appropriate valves for the individual burners and pilots are closed to keep unburned fuel from entering the furnace. Unburned fuel creates a potential explosion hazard. For this furnace, the steam purging valves are closed before the pilots are lit. But the stack damper should be left in the full open position to provide adequate draft for light-off. It may also be necessary to leave the burner air registers open to allow enough combustion air into the burner. For this startup, all the burners are going to be lit. However, at reduced firing rates, some of the burners may not be used. At reduced firing rates, the air registers for the unused burners are closed to keep unwanted air out. The pilot fuel may come from the same source as the burner fuel, or it may come from a separate source, which is the case here. In either case, the appropriate fuel valve is open to get fuel to the pilots. A pilot header routes the fuel to the individual pilots. Before the pilots are lit, there are some safety considerations to keep in mind. For example, it's important to have the necessary safety gear. Face shields and fire-resistant gloves are often required. Different facilities have different safety requirements. For this furnace, 2 operators are needed to light the pilots, one to open the pilot valve and another to insert a torch into the burner. In this case, a non-combustible absorbent material is wrapped around the end of a torch, and it's soaked with a fairly heavy fuel, like kerosene. A lighter fuel, like gasoline, might ignite too easily. When the operator with the torch is ready to light, he gives the go-ahead to the operator at the pilot valve. With the torch in the burner, the pilot valve is opened. The pilot should ignite easily. The remaining pilots are lit just like the first one. It's a good safety practice to light all of the pilots before lighting any of the burners. If a pilot won't light, you could have unburned fuel in the furnace, which is explosive. If a pilot fails to light, you may have to close everything down and purge the furnace again to get unburned fuel out. When the pilots are lit, the burners can be ignited. To do that, the fuel valves will have to be lined up as indicated in the startup procedures. Outside operators and control room operators work together to light off the burners. The goal is to bring the charge temperature up gradually, so metal parts won't suffer damage from heating up and expanding too fast. In addition, the process fluid that's circulating through the tubes will carry away some of the furnace heat. This also helps prevent abnormal expansion in the furnace. The control room operator usually has manual control of the firing rate during startup. This lets him bring the furnace up to operating temperature at the proper rate. In gas-fired furnaces, the fuel header is pressured up with fuel gas before the burners are lit. This makes it easier to ignite the burners. To get fuel to the header, the operator opens the fuel flow control valve to the proper position. Header pressure is monitored from the control room and at the furnace. When the header pressure is right, the outside operators light off the first burner. The fuel valve for the burner is opened slowly until the burner lights off the pilot. The burner produces a distinctive sound when it lights. With experience, you'll get to know what to listen and look for. It may be necessary to increase fuel flow to the burner to get it to light. When more heat is needed for the process fluid, the control room operator gives the okay to light another burner. The remaining burners are lit like the first one. To reduce the risk of explosion, burners should always be lit from their pilots, not from adjacent burners. The operators will light the burners in a staggered pattern. The burners are lit in a staggered pattern to provide a good distribution of heat in the furnace. If one burner goes out while the others stay lit, it may be necessary to shut off the fuel to that burner for a few minutes to let the fuel burn off and then relight the burner. When all the burners are lit, fuel flow will have to be increased to reach the desired charge temperature. As fuel flow is increased, the air registers may have to be adjusted to get the proper flame size and pattern. To do this, one operator checks the flames while the other works the registers. They use signals to communicate. When the burners are firing properly and the process fluid is at its normal temperature, the system is switched over to automatic control. From now on, changes in the process fluid outlet temperature will automatically trigger changes in the amount of fuel sent to the burners. We just saw a startup procedure for a furnace with gas burners. The overall startup is basically the same for furnaces with oil burners or combination burners. But when it comes to lighting the burners, the procedure can vary depending on the type of burner. So we need to see the main steps involved in lighting oil burners and combination burners. To do this, we'll assume that the pilots have already been lit, but that the burner fuel valves are still closed. You may recall that oil burners have atomizers or oil guns that break the fuel oil into a mist so it will burn easier. This burner has a steam atomizer. What do you suppose is typically the first step in putting it into service? The operator opens steam valves to get steam flowing to the atomizer. The steam may have moisture in it. Moisture in the steam may produce a sparky, improper flame pattern. So before the burner is lit, steam flow through the atomizer should continue long enough to remove the moisture. When the moisture's been removed, the steam coming out of the atomizer should be nearly invisible. When the steam is dry, the operator opens the oil valves to allow oil to flow to the atomizer. After the atomized oil ignites off the pilot, the steam valve and the oil valve can be adjusted to produce a proper flame pattern. Another type of burner you may find in furnaces is a combination burner, which can burn gas and oil. If both fuels are burned, the gas burning part is usually lit first and the oil is lit later. This is a typical sequence because gas is easier to ignite than oil. The startup procedures we saw apply to natural draft furnaces, but most of the same steps are also followed when starting a balanced draft furnace. You may recall that a balanced draft furnace has two fans, a forced draft fan, which provides air for the burners, and an induced draft fan, which removes the exhaust gases from the furnace. In addition, most balanced draft furnaces have an air preheater. It uses the heat from combustion gases to warm the air sent to the burners. Using warm combustion air improves efficiency because more heat is transferred to the process fluid and less heat goes to heating the incoming air. If your plant uses balanced draft furnaces, it will probably have detailed startup procedures. But the key point to remember is that the fans and the air preheater will have to be part of the startup. In this topic, we saw how furnaces are normally started up. We looked at startup preparations. We saw how to establish the flow of process fluid, and we learned the basic procedures involved in lighting burners. Take a minute now to try a few practice questions on this information. For many furnaces, the last thing done before lighting the burners is purging. Purging the furnace removes any combustibles or unburned fuel. Unburned fuel can explode when the burners are ignited. In many cases, furnace startup actually begins with establishing the flow of process fluid or charge. This step should normally be done before the burners are lit. Otherwise, the empty tubes that carry the process fluid could become overheated by the burner flames. The first main step in lighting the burners is to light the pilots. To be safe, the operator checks that all the appropriate valves for the individual burners and pilots are closed to keep unburned fuel from entering the furnace. Unburned fuel creates a potential explosion hazard. For this furnace, the steam purging valves are closed before the pilots are lit, but the stack damper should be left in the full open position to provide adequate draft for light-off. It may also be necessary to leave the burner air registers open to allow enough combustion air into the burner. Planned shutdowns may be done when a furnace is taken out of service for scheduled maintenance or repairs, or perhaps when there's a unit turnaround. That is, when the entire unit is shut down for maintenance or repair work. A planned shutdown may also be performed if there are problems or upsets in other unit processes, even though the furnace may be running okay. The objective of a planned shutdown is basically the opposite of a startup. That is, you want to bring the temperatures and the firing rate down gradually. In general, this is done by turning off the burners one at a time and then turning off all the pilots at once. During shutdown, when furnace temperatures are lowered, the refractory and metal parts in the furnace contract. Slowly decreasing the temperatures will reduce the chances that parts of the furnace will be damaged from cooling and contracting too quickly. Planned shutdown sequences are not exactly the same in all cases, but a lot of the important major steps are common to most furnaces. If automatic control systems are in operation, they may be switched to manual. This gives the furnace operators more direct control over the firing rate as the temperatures are lowered. The fuel flow to the burners can be reduced slowly to bring down the process fluid outlet temperature. The operator keeps his eye on the fuel pressure to make sure it doesn't drop too fast. Reducing the fuel pressure slowly helps decrease the outlet temperature gradually. Can you think of another reason why you don't want the fuel pressure to drop too fast? If fuel pressure drops too fast, there's a risk of flameouts. That is, the burners may go out too soon, leaving unburned fuel in a hot furnace, a dangerous explosive condition. When the outlet temperature has dropped a predetermined amount, the outside operator is told to shut off the first burner. He does this by closing the burner's isolation valve. When the outlet temperature has dropped by another predetermined amount, the control room operator gives the go-ahead to take out another burner. The burners are turned off in a staggered pattern to keep the heat evenly distributed in the furnace during the shutdown. For this furnace, when the last burner is turned off, isolation valves on either side of the flow control valve are closed manually to prevent fuel from leaking into the furnace. Then the isolation valves for the burner pilots can be turned off. After the last pilot is out, the main fuel supply for the pilots is turned off. Often, the process fluid is kept flowing for a while after the burners are off. Circulating fluid carries heat away from the furnace, which allows for a more controlled cool down. The pump for the process fluid is shut off, and the valves that regulate the process fluid flow are closed according to shutdown procedures. Sometimes the process fluid is removed from the tubes at shutdown. If the fluid contains carbon or coke, the inside of the tubes may have to be cleaned and decoked. Carbon deposits in the tubes may create heat transfer and flow problems. In this system, valves route steam and air through the process fluid lines to burn off the carbon deposits and carry them out of the lines. The fuel lines and the process fluid lines may have to be blinded as well. And with many furnaces, it's standard practice to purge the furnace again after it is cooled down. While a planned shutdown allows a furnace to be cooled gradually, an emergency shutdown is different. The furnace has to be shut off right away to reduce the risks of danger and damage. During emergencies, the furnace operator's knowledge and experience are really put to the test. There are several conditions that can lead to an emergency shutdown. One possibility is an abnormally high stack temperature. This could result from a tube rupture or from a fire in the convection section. A low process fluid flow rate can also trigger an emergency shutdown. If the flow rate is too low in any one pass, there's a danger that the tubes in that pass could overheat and rupture. Another potential emergency situation is insufficient fuel pressure in the fuel header. Without adequate fuel flow to the burners, there's a risk of flameouts and explosions. If the burners go out, fuel could ignite off the hot refractory and explode. An electrical power outage at the plant can also set in motion an emergency shutdown procedure. Without electrical power, you may lose a lot of your furnace instrumentation, as well as any electric motors. Charge pumps, for example, may be electrically driven. Many furnaces are equipped with automatic shutdown systems that are activated if emergency conditions arise. In some systems, the stack damper will be automatically opened all the way if there's an emergency. Opening the stack damper all the way allows unburned combustibles to flow out of the furnace quickly. This reduces the chance of a furnace explosion. In addition, you'll find automatic safeguards for the fuel supply system. This emergency shutoff valve, for example, stops fuel flow to the furnace if either the fuel header pressure or the process fluid flow rate gets too low. This is a different type of system. It's called a double block and bleed arrangement, and it's often used with gas-burning furnaces. There are 2 block or isolation valves and a bleed valve. In an emergency, the block valves automatically shut off. This stops fuel flow to the burners. Then the bleed valve automatically opens. In this system, the bleed valve diverts the fuel that's trapped between the 2 block valves to a flare where it's burned off safely. Many emergency fuel valves have a latch that has to be reset manually to open the valve again. The systems we've seen are designed to work automatically. However, there are times when operators have to take control of the furnace during an emergency. Typically, when this happens, the burners and pilots are shut off as quickly as possible, but the steps you'll need to follow will depend on the nature of the emergency. To be prepared for any situation, you should become familiar with your plant's emergency shutdown procedures. In this topic, we focused on furnace shutdowns, including both planned and emergency shutdowns. Take a minute now to answer a couple of practice questions on this material. The objective of a planned shutdown is basically the opposite of a startup. That is, you want to bring the temperatures and the firing rate down gradually. In general, this is done by turning off the burners one at a time and then turning off all the pilots at once. There are several conditions that can lead to an emergency shutdown. One possibility is an abnormally high stack temperature. This could result from a tube rupture or from a fire in the convection section. A low process fluid flow rate can also trigger an emergency shutdown. If the flow rate is too low in any one pass, there's a danger that the tubes in that pass could overheat and rupture. Another potential emergency situation is insufficient fuel pressure in the fuel header. Without adequate fuel flow to the burners, there's a risk of flameouts and explosions. If the burners go out, fuel could ignite off the hot refractory and explode. An electrical power outage at the plant can also set in motion an emergency shutdown procedure.